There's a hidden world all around us, one so strange, so utterly bizarre, that it makes the wildest science fiction seem tame by comparison. Picture this: particles that vanish and reappear in an instant, forces that reach across the universe without ever touching, and a cosmic fabric so flexible it twists and bends like a sheet of rubber. This isn't fantasy. This is the quantum cosmos, a realm where the rules of reality, as we know them, don't just bend, they shatter. And the most astonishing part: these aren't just abstract ideas tucked away in a physicist's notebook. They're the invisible threads weaving the very fabric of our existence, shaping everything from the stars above us to the devices in our hands. What if I told you there are 22 unseen forces and phenomena operating behind the scenes of our universe, phenomena so profound they challenge our very understanding of space, time, and matter? Some, like quantum entanglement, link particles across vast distances in ways Einstein himself called spooky. Others, like dark energy, silently push the cosmos apart at an ever-increasing pace, as if the universe itself is in a hurry to escape its own shadow. These aren't just curiosities for scientists in lab coats. They're clues to the deepest mysteries of reality, waiting to be unraveled. So why does this matter to you? Because the quantum cosmos isn't some distant, untouchable realm. It's the hidden architecture of everything. It's the reason your computer works, the force guiding galaxies, the answer to questions we've been asking since the dawn of human curiosity. And today, we're going on a journey, one that will take us beyond the visible, beyond the ordinary, and into a world where the impossible becomes possible. By the time we're done, you'll see the universe in a whole new light. So let's begin. The quantum cosmos is waiting. Quantum entanglement is one of the most baffling yet beautiful phenomena in the quantum world. Imagine two particles, let's call them Alice and Bob, born from the same quantum event, instantly bound together no matter how far apart they drift. If Alice spins clockwise, Bob instantly spins counterclockwise, even if they're on opposite sides of the galaxy. This isn't a delayed signal traveling at the speed of light. It's instantaneous, as if space and time don't apply to them. Einstein famously dismissed this as spooky action at a distance because it clashed with everything classical physics told us about how the universe should work. Yet, countless experiments have proven entanglement is real, leaving scientists both thrilled and perplexed. What makes this even stranger is that entanglement isn't just a quirky lab observation. It's the foundation of emerging technologies like quantum computing and ultra-secure communication. In quantum computers, entangled particles process information in ways traditional bits never could, solving problems in minutes that would take conventional supercomputers centuries. Meanwhile, quantum encryption uses entanglement to create unbreakable codes, where any attempt to spy on the message instantly alters it, alerting the sender. But beyond these practical breakthroughs, entanglement hints at something far more profound, a hidden layer of connection woven into the fabric of reality itself. Some physicists speculate that entanglement might be a glimpse into a deeper, underlying structure of the universe, one where separation is an illusion and everything is fundamentally linked. Think of it like a cosmic symphony where every particle plays its note in perfect harmony with every other, no matter how vast the distance. If that's true, it could rewrite our understanding of space, time, and even consciousness. Could entanglement be the thread stitching the universe together, or is it just the first clue in a much larger mystery waiting to be unraveled? One thing's for certain, the quantum world has more surprises in store. Now let's turn our attention to something even more mysterious, an invisible force sculpting the cosmos while remaining completely hidden from our eyes. Dark matter doesn't emit light, absorb it, or reflect it, yet its gravitational grip holds entire galaxies together. Think of it like the wind. You can't see it, but you see its effects everywhere. Stars on the outer edges of galaxies rotate at speeds that should fling them into the void, yet something unseen keeps them anchored. That something is dark matter, an enigmatic substance making up 27% of the universe, 5 times more than all the ordinary matter we can see and touch. Scientists first suspected its existence nearly a century ago when astronomer Fritz Zwicky noticed galaxies in the Coma cluster moving too fast to be held together by visible matter alone. He called it Dunkel Materie, dark matter, and though his peers dismissed it at the time, modern observations have confirmed his radical idea. From the graceful swirl of spiral galaxies to the colossal web of galaxy clusters stretching across the cosmos, dark matter's fingerprints are everywhere. But here's the puzzle. Despite decades of searching, we've never directly detected it. Teams of researchers are hunting for dark matter particles in abandoned mines deep underground, where sensitive detectors wait for the faintest whisper of a collision. Others scan the skies with space telescopes, hoping to catch indirect clues in the way dark matter bends light around it. Some theories suggest dark matter could be made of WIMP, weakly interacting massive particles, while others propose Axions, ultra-light particles flowing through the universe like an invisible river. But what if dark matter isn't just one thing? What if it's an entire hidden ecosystem of particles, each with its own role in shaping reality? The implications are staggering. If dark matter interacts with itself in ways we don't yet understand, it could form shadowy structures, dark galaxies, dark stars, even dark planets existing parallel to our own visible universe. Some theories even suggest dark matter might have its own forces, its own particles, its own rules. Imagine a ghostly mirror world, intertwined with ours yet forever out of reach. Whatever the truth, one thing is clear: dark matter isn't just a cosmic placeholder. It's the unseen architect of the universe, quietly shaping everything we know and everything we don't. If dark matter is the unseen glue holding galaxies together, dark energy is the mysterious force tearing the cosmos apart at the seams. In the late 1990s, astronomers made a discovery that turned our understanding of the universe upside down. By observing distant supernova, they found that not only is the universe expanding, it's accelerating, as if some invisible hand is pressing harder on the cosmic gas pedal with each passing moment. That hand belongs to dark energy, an enigmatic force making up a staggering 68% of the universe's total content. Unlike gravity, which pulls things together, dark energy behaves like an anti-gravity, pushing space itself apart faster and faster. What makes dark energy so baffling is that we don't even know what it is. Some theories suggest it's a property of empty space itself, a sort of cosmic tension woven into the fabric of reality, growing stronger as the universe expands. Others propose it could be an entirely new form of energy, one that doesn't behave like anything we've ever encountered. Then there's the most dramatic possibility: the Big Rip. If dark energy's repulsive force keeps strengthening over time, it could eventually overpower every other force in nature, first tearing galaxies apart, then stars, then planets, and finally even atoms themselves. The universe would end not with a whimper, but with a violent, unstoppable shredding of spacetime. Yet for all its destructive potential, dark energy might also hold the key to our cosmic origins. Some physicists believe it's closely tied to another mysterious event, the Big Bang's rapid inflationary phase, when the universe expanded exponentially in a fraction of a second. Could dark energy be the lingering echo of that primordial expansion? Or is it something entirely new, a force we've only just begun to glimpse? Right now, telescopes like the Dark Energy Survey and the upcoming Nancy Grace Roman Space Telescope are mapping the universe's expansion with unprecedented precision, hunting for clues in the way galaxies cluster and light bends across billions of light years. What they find could rewrite the laws of physics. If dark energy changes over time, it might hint at undiscovered dimensions or hidden fields permeating the cosmos. Some even speculate it could be linked to the quantum vacuum, where particles flicker in and out of existence, generating energy from nothing. But here's the twist: the more we learn, the more we realize how much we don't know. Dark energy isn't just a puzzle, it's a doorway, one that could lead us to a deeper understanding of reality itself. And as we stand on that threshold, we're left with a humbling thought: the universe isn't just expanding. It's running away from us, carrying its secrets into the void. Wormholes sound like something straight out of science fiction tunnels burrowing through the fabric of space-time, connecting distant corners of the universe in the blink of an eye. But the wildest part, they're not just fantasy. Einstein's equations of general relativity actually allow for their existence. Picture space-time as a stretched rubber sheet, with massive objects like stars creating dips in the fabric. Now imagine folding that sheet so two distant points touch, then punching a hole through them. That's the essence of a wormhole, a cosmic shortcut where entering one end could spit you out light years away, or even in a completely different universe. The catch: wormholes, if they exist, would be incredibly unstable. Without some form of exotic matter, a hypothetical substance with negative energy, they'd collapse the instant anything tried to pass through. Negative energy sounds impossible, but quantum mechanics hints it might not be. In the quantum vacuum, particles and antiparticles constantly flicker in and out of existence, creating fleeting bursts of negative energy. Could we harness this to prop open a wormhole? Some theories suggest advanced civilizations might already be doing just that, using these tunnels as interstellar highways. But here's where it gets even stranger. At the smallest scales, space-time isn't smooth. It's a frothing, bubbling quantum foam, where tiny wormholes might constantly form and vanish. If we could somehow stabilize one of these microscopic passages, could we stretch it into a usable gateway? The idea pushes the boundaries of physics, blending relativity with quantum theory in ways we're only beginning to explore. And while wormholes remain theoretical for now, they force us to ask profound questions. Is the universe more connected than we realize? Are there hidden doorways woven into the fabric of reality, waiting to be unlocked? One thing certain: wormholes challenge our understanding of distance, time, and even causality. If you could step through one and emerge before you left, would you create a paradox? Or does the universe have laws we haven't discovered yet to prevent such chaos? These aren't just thought experiments. They're clues to a deeper truth, that space-time might be far more malleable, far more mysterious than we ever imagined. And as we peer into the quantum foam, where space itself churns with potential, we're left wondering, could the key to unlocking the cosmos lie in these fleeting, phantom tunnels? Empty space isn't empty at all. It's a boiling, churning sea of energy, alive with particles that flicker into existence and vanish before we can even detect them. This is the quantum vacuum, where so-called nothingness is anything but, at the tiniest scales, pairs of virtual particles, matter and antimatter, constantly emerge from the void only to annihilate each other in a flash. These quantum fluctuations aren't just theoretical quirks. They create real, measurable forces that shape the behavior of everything around us. Take the Casimir effect. Place two uncharged metal plates incredibly close together in a vacuum, and they'll snap toward each other as if pulled by an invisible hand. Why? Because the space between them is too narrow for certain virtual particles to form, creating a pressure imbalance that pushes the plates together. It's proof that empty space is anything but passive, but here's where it gets truly mind-bending. Some physicists believe these fleeting particles might be the source of dark energy, the mysterious force accelerating the universe's expansion. Imagine the vacuum of space as an infinite ocean, with each tiny ripple contributing to a vast, unstoppable tide pushing galaxies apart. If true, it would mean the universe is being stretched by the restless energy of nothingness itself. That raises an electrifying question. Could we harness this zero-point energy? The idea isn't science fiction. Calculations suggest the energy density of the quantum vacuum is unimaginably vast. A single cubic centimeter of empty space might contain more energy than all the matter in the observable universe combined. The challenge, tapping into it, is like trying to bottle a mirage. These particles vanish almost instantly, and extracting usable energy would require stabilizing them, something no known technology can achieve. Yet, that hasn't stopped scientists from dreaming. Some theories propose manipulating the vacuum structure with ultra-strong electromagnetic fields or exotic materials, while others explore whether advanced civilizations might already be using zero-point energy as a power source. Even if we never harness it, quantum fluctuations hint at something profound. The universe is built on a foundation of chaos and potential, where particles dance in and out of existence, weaving reality itself from the fabric of uncertainty. This constant flickering might even hold clues to the birth of the cosmos. Some models suggest the Big Bang itself could have been triggered by a massive quantum fluctuation, a random burst of energy so powerful it birthed space and time. If that's true, then every star, every planet, every one of us owes our existence to the restless hum of the quantum vacuum. It's a reminder that nothing is ever truly still, and that even in the deepest void, the universe is humming with hidden life. Light and matter play a game of cosmic hide and seek with reality itself, one where the rules change depending on how we look at them. This is wave-particle duality, the baffling phenomenon where photons, electrons, and even entire molecules switch between behaving like solid particles and spread out waves. The most iconic demonstration of this is the double-slit experiment, a deceptively simple setup that shatters our everyday intuition. Shine light through two narrow slits onto a screen, and instead of two bright stripes, you get an interference pattern, a series of light and dark bands that only waves could produce. But here's where it gets weird. Fire single photons at the slits one by one, and over time, that same wave pattern emerges. It's as if each photon passes through both slits simultaneously, interfering with itself. Now replace the light source with electrons particles with mass, and the same thing happens. Even more astonishing, the moment you place a detector to observe which slit each electron passes through, the interference pattern vanishes. The electrons suddenly choose to act like particles, leaving two clean stripes instead of a wave's ripple. It's as if reality rearranges itself based on whether we're watching. This isn't a quirk of measurement error, it's a fundamental property of the quantum world. Particles exist in a haze of possibilities until an observation forces them to pick a state. Some interpretations suggest consciousness itself might play a role in collapsing these possibilities into concrete reality, a notion that blurs the line between observer and observed. Yet wave-particle duality isn't just a philosophical puzzle, it's the engine powering technologies we use every day. Electron microscopes leverage this duality by using electrons as waves to image objects too small for light waves to resolve. Solar panels absorb photons as particles to knock electrons loose and generate electricity. Even the lasers in your Blu-ray player rely on light's wave nature to encode data with precision. But beneath these practical applications lies a deeper mystery. What does it mean for something to be both a localized particle and a spread-out wave at the same time? This brings us to superposition, the quantum principle where particles exist in multiple states simultaneously until measured. Think of Schrödinger's famous, if morbid, thought experiment: a cat in a box, simultaneously alive and dead until someone lifts the lid. While we don't see such extremes in the macroscopic world, at quantum scales, superposition is very real. Quantum computers exploit this by using qubits particles that can be 0, 1, or both at once to perform calculations at dizzying speeds. But superposition also raises a radical question. Is the universe fundamentally uncertain until observed, or are we missing a hidden layer of reality that governs these seemingly random choices? One provocative theory proposes that every possible outcome of a quantum event does happen, just in parallel universes. In this many worlds interpretation, the wave never collapses. Instead, reality branches endlessly, with each version of you witnessing a different result. Another idea suggests particles sample all possible paths through spacetime, as if reality is a tapestry woven from every conceivable thread. Whether these theories hold up or not, one thing is undeniable. Wave-particle duality forces us to confront the unsettling truth that at its core, the universe refuses to play by the neat, deterministic rules we once assumed. It thrives on ambiguity, dancing between states like a cosmic trickster, and the closer we look, the more elusive its true nature becomes. Quantum superposition turns our everyday logic upside down. Picture a spinning coin in mid-air, not heads, not tails, but both at the same time, its fate undecided until it lands. In the quantum realm, particles live in this suspended state of both-ness until something or someone forces them to pick. This isn't just theoretical. Scientists have observed electrons, photons, and even entire molecules existing in multiple places or states simultaneously. Take the famous Schrödinger's cat paradox. A feline trapped in a box with a lethal quantum trigger is, mathematically speaking, both alive and dead until the box opens. While we don't see cats or anything at human scales in such blatant superposition, the principle holds at the atomic level, and it's the secret sauce behind quantum computing. These machines don't rely on ordinary bits, which are either 0 or 1. Instead, they use qubits quantum bits that can be 0, 1, or any probabilistic mix of both at once. A single qubit is like a dimmer switch with infinite settings between off and on. Link multiple qubits together through entanglement, and their combined states explode exponentially. A traditional computer checking 1,000 possibilities one by one might take hours. A quantum computer explores them all simultaneously, as if running 1,000 calculations in parallel. This could revolutionize fields from drug discovery to cryptography, cracking problems that would take classical machines longer than the age of the universe to solve. But here's the haunting question. When a superposition finally collapses into a single outcome, who or what makes the call? The many worlds interpretation offers a dizzying answer. Maybe nothing does. Instead, every possible outcome branches into a new universe. In one reality, the cat lives. In another, it dies. Your measurement didn't force a choice. It just placed you on one path of an endlessly splitting cosmic tree. This isn't science fiction. Some physicists argue it's the simplest way to explain why quantum math works without adding mysterious observer effects. If true, there are versions of you who witnessed every possible outcome of every quantum event, their lives unfolding in unseen dimensions, yet alternative theories abound. Hidden variable models suggest particles carry unseen instructions dictating their behavior, like a cosmic script we haven't decoded. Collapse theories propose superposition breaks down spontaneously, with no observer needed. And then there's the radical idea that consciousness itself plays a role, that reality remains fluid until a mind interacts with it. Each interpretation has its champions and flaws, but they all agree on one thing: superposition reveals a universe far stranger than the clockwork cosmos Newton imagined. Now imagine a phenomenon so bizarre it might connect these parallel worlds. Quantum tunneling allows particles to bypass barriers as if they're ghosting through walls. Place an electron in front of an impenetrable energy wall, and there's a chance it'll suddenly appear on the other side. No hole, no climb, just an impossible leap. This isn't a fluke. It's how stars fuse hydrogen into helium, how your smartphone's transistors work, and why some scientists speculate tunneling might be particles briefly borrowing energy from alternate realities. Could this be the thread stitching the multiverse together, or just another clue that at the smallest scales, the universe operates by rules we're only beginning to glimpse? One thing's certain: superposition forces us to confront the unsettling fluidity of reality. The quantum world doesn't deal in absolutes, it thrives on potential, a shimmering haze of maybes waiting to crystallize into certainty. And as we peer deeper, we're left wondering, if particles can be everywhere and nowhere at once, what other impossibilities might the universe be hiding in plain sight? Quantum tunneling defies everything we thought we knew about obstacles. Imagine throwing a ball at a wall. Classical physics says it'll bounce back every time. But in the quantum world, there's a chance the ball could suddenly appear on the other side, as if the wall weren't there at all. That's tunneling in action. Particles like electrons don't always follow the rules of can and can't. Instead, they exploit the fuzzy probabilities of quantum mechanics, vanishing from one side of a barrier and reappearing on the other without ever crossing the space in between. This isn't just a laboratory curiosity. Without tunneling, the sun wouldn't shine. Hydrogen nuclei in stars repel each other due to their positive charges, but tunneling lets them bypass that repulsion, fusing into helium and releasing the energy that lights our skies. Your smartphone owes its existence to tunneling. 2 transistors in modern chips rely on electrons ghosting through barriers at microscopic scales. Even your DNA mutates partly due to protons tunneling between molecules, driving the slow march of evolution. The implications stretch far beyond Earth. Some astrophysicists speculate tunneling could explain rare, high-energy cosmic events like particles escaping the crushing grip of neutron stars or even black holes. Speaking of which, black holes might be tunneling's ultimate test. Their event horizons are the universe's most formidable barriers, yet quantum mechanics suggests particles can tunnel out as Hawking radiation, slowly evaporating these cosmic monsters over eons. Could this mean black holes are leaking information into the universe, defying their reputation as eternal traps? But here's the real mind bender: tunneling might hint at a multiverse. Some theories propose particles borrow energy from parallel realities to leap barriers, paying it back instantaneously like a cosmic loan shark operating outside time. Others suggest tunneling reveals space-time's graininess, where particles exploit tiny gaps in the fabric of reality itself. Whatever the truth, one thing's clear: the universe has a cheat code, and quantum tunneling is its signature move. So the next time you charge your phone or bask in sunlight, remember, you're witnessing the impossible made ordinary, thanks to particles that refuse to play by the rules. Black holes aren't just cosmic vacuum cleaners, they're information shredders, or so we once thought. When an object crosses a black hole's event horizon, it seems to vanish from the universe, leaving behind only mass, charge, and spin. But here's the problem. Quantum mechanics insists information can never truly be destroyed. Every particle, every interaction leaves a trace, a cosmic paper trail that should, in theory, be recoverable. This clash between quantum theory and general relativity is the black hole information paradox, and it's one of the most heated debates in modern physics. Stephen Hawking's groundbreaking work added fuel to the fire. He showed black holes aren't entirely black, they emit radiation, slowly evaporating over eons. But if a black hole vanishes, what happens to all the information it swallowed? Hawking initially argued it's lost forever, violating quantum mechanics' core tenets. Later, he changed his mind, suggesting information might leak back out encoded in the radiation, scrambled beyond recognition. Imagine burning a book and claiming the smoke carries its contents, just in a form no one can read. Enter the holographic principle, a radical idea proposing that all the information inside a black hole is actually smeared across its event horizon like a cosmic fingerprint. Instead of a three-dimensional interior, everything is encoded on a two-dimensional surface, a hologram of reality itself. If true, the universe might work the same way, with our 3D existence projected from a hidden boundary we can't see. Then there's the firewall hypothesis, suggesting the event horizon isn't a gentle threshold but a searing wall of energy that obliterates anything crossing it, preserving information by turning infalling matter into pure data. But these solutions raise new questions. If firewalls exist, Einstein's equivalence principle, the idea that free-falling observers feel no gravity, would be wrong. And if information escapes via Hawking radiation, how does it break free from a region even light can't escape? The answer might lie in quantum entanglement, with particles inside and outside the black hole remaining mysteriously linked, weaving a hidden network that ferries information to safety. This paradox isn't just academic. Solving it could reveal the missing link between gravity and quantum mechanics, a theory of everything. Some researchers now speculate black holes might be cosmic laboratories, their extremes exposing the fabric of spacetime in ways we can't replicate on Earth. Others wonder if the very notion of information needs redefining. Could it be that the universe keeps its books in a language we haven't deciphered yet? As the debate rages, one thing is clear. Black holes aren't just swallowing matter, they're challenging our understanding of reality itself. And the key to unlocking their secrets might not lie in their darkness, but in the faint, coded whispers of the radiation they leave behind. Gravity keeps our feet on the ground and planets in orbit, but at the quantum scale, it vanishes from the equations entirely. This glaring gap between Einstein's general relativity and quantum mechanics is the single biggest unsolved puzzle in physics, and solving it might require rewriting the laws of reality. Enter quantum gravity, the quest to explain how the universe's gentlest yet most far-reaching force operates at the tiniest scales. If successful, it could reveal whether spacetime itself is stitched together from discrete, indivisible chunks like a cosmic pixel grid, or if gravity emerges from something even stranger. String theory offers one dazzling possibility. Imagine every particle isn't a point but a vibrating filament of energy, with different vibrations producing electrons, quarks, or even the hypothetical graviton gravity's answer to the photon. These strings would dance through 10 or 11 dimensions, their harmonies weaving the fabric of reality. The math is elegant, but there's a catch. No experiment has yet confirmed these extra dimensions or strings. Critics argue it's more philosophy than physics. while proponents see it as a universe-sized symphony waiting to be heard. Then there's loop quantum gravity, which paints spacetime as a network of interconnected loops. Think of a sprawling, dynamic spiderweb where each intersection represents a tiny volume of space. Here, gravity isn't a force mediated by particles but a property of spacetime's granular structure. When two black holes merge, their collision might send ripples through this web, creating the gravitational waves we've detected. But loops come with their own mysteries. What happens at the center of a black hole where this web tangles into a knot of infinite density? The hunt for gravitons adds another layer of intrigue. These hypothetical particles would carry gravitational force just as photons carry electromagnetism, but they'd be absurdly hard to detect. A single graviton's effect is weaker than a neutrino's whisper, so faint that catching one might require a detector the size of Jupiter. Yet some physicists dream of spotting them in the aftermath of cosmic cataclysms, like colliding neutron stars or the Big Bang's echoes. What if gravity isn't fundamental at all? Emerging theories suggest it might be an emergent phenomenon, like temperature arising from countless atoms' motion. In this view, spacetime itself could be a hologram, a projection from a lower dimensional reality where gravity doesn't exist. It's a concept that bends the mind as much as spacetime bends light. The stakes couldn't be higher. Unifying gravity with quantum mechanics wouldn't just fill a textbook gap. It could explain the birth of the universe, the fate of black holes, and whether time itself is quantized. It might even reveal hidden dimensions curled like origami around us. Until then, quantum gravity remains the ultimate frontier, a puzzle that dares us to rethink everything we know about the cosmos, from the smallest loops to the vast, echoing voids between galaxies. What if time isn't the one-way street we've always assumed? Enter retro-causality, the mind-bending idea that the future might reach back and tweak the past. At first glance, it sounds like pure science fiction, but quantum mechanics has a habit of turning fiction into fact. Consider the delayed choice experiment, a twist on the classic double-slit setup. When scientists decide whether to measure a photon's path after it's already passed through the slits, the particle seems to choose whether it behaved as a wave or a particle retroactively, as if the future measurement rewrote its history. It's like a detective altering a crime scene by the mere act of investigating it. This isn't just a quirk of light. Similar effects appear in quantum entanglement, where measuring one particle instantly defines its partner's state, even if that partner's fate was sealed billions of years ago in the distant cosmos. Some interpretations suggest these particles aren't communicating faster than light. Instead, their connection might transcend time entirely, with future observations shaping past events. Imagine tossing a coin today and next week's weather determining whether it landed heads or tails. That's the level of temporal weirdness we're dealing with. The implications are staggering. If retro-causality is real, it could pave the way for quantum systems that pre-compute solutions by leveraging future states, making today's supercomputers look like abacuses. Communication might break free of light speed limits, with messages encoded in events that haven't happened yet. But before we rewrite the textbooks, there's a catch. These effects only surface in carefully controlled quantum experiments. Scaling them to practical use would require bending causality without shattering it, a puzzle that's equal parts thrilling and terrifying. Now, let's turn to a subtler force, one so pervasive we rarely notice it, yet it shapes the universe from the quantum foam to galactic clusters. Vacuum energy isn't empty. It's a seething ocean of potential where particles flicker in and out of existence, borrowing energy from nothingness itself. This isn't theoretical. The Casimir effect proves it. Place two metal plates nanometers apart in a vacuum, and they're pushed together by the sheer pressure of virtual particles popping into being outside them. It's as if the universe is constantly bubbling with creative chaos, and we're only seeing the calm surface. What's truly astonishing is how this hidden energy might connect to retro-causality. Some models suggest vacuum fluctuations could create tiny time loops, where particles briefly interact with their future or past selves. If true, the quantum vacuum isn't just a backdrop, it's an active participant in the flow of time, weaving causality into something far more flexible than we ever imagined. Whether these ideas hold up or not, one thing's clear: the universe has a flair for the dramatic, and its greatest tricks are still waiting in the wings. The Casimir effect is like the universe's version of a magic trick, one where empty space itself becomes an invisible puppeteer, pulling objects together without any visible strings. Picture two uncharged metal plates placed so close in a vacuum that there's barely room for a single atom between them. Classically, nothing should happen. But in the quantum world, these plates snap toward each other as if tugged by ghostly hands. Why? Because the tiny gap between them restricts the kinds of virtual particles that can flicker into existence there. Outside the plates, the quantum vacuum buzzes with limitless possibilities, particle-antiparticle pairs popping in and out of reality. But inside that narrow space, only certain wavelengths fit, creating a pressure imbalance that pushes the plates together. It's not a force in the traditional sense. It's the universe's way of saying even nothing is never truly quiet. This effect isn't just a laboratory curiosity. It's a blueprint for technologies that could reshape our future. Imagine nanoscale machines where Casimir forces replace gears and levers, allowing components to self-assemble with atomic precision. Researchers are already exploring how to harness these quantum whispers to create frictionless bearings or ultra-sensitive sensors. But the real sci-fi potential lies in propulsion. Some theoretical models suggest that manipulating Casimir forces could generate negative energy densities, a key ingredient for warp drives. Yes, the same kind of warp drives that could bend spacetime and make interstellar travel a reality. The catch: we'd need to engineer materials with properties that don't yet exist, like perfect mirrors that reflect every possible quantum fluctuation. Yet the deepest implications of the Casimir effect might not be technological. They could be cosmic. If empty space crackles with this much latent energy, what does that mean for the universe's expansion? Some calculations suggest the quantum vacuum's energy density should be astronomically higher than what we observe, a discrepancy known as the cosmological constant problem. It's as if the universe's math is off by a factor of 1 followed by 120 zeros. This isn't just a rounding error. It hints that we're missing something fundamental about how gravity and quantum mechanics intertwine. Now, let's turn to a phenomenon that challenges one of physics' most sacred laws: thermodynamics. Normally, entropy always increases. The universe tends toward disorder, like a shattered glass that never reassembles itself. But in the quantum realm, particles sometimes defy this rule, temporarily reversing entropy in ways that could rewrite our understanding of energy and time. Negative energy sounds like something from a physicist's wildest dreams, a state where the energy density of a system drops below zero, defying the very notion of empty space. Picture a stretched rubber band that, instead of snapping back, pushes outward with anti-tension. This isn't just theoretical mischief. Negative energy could be the secret ingredient for stabilizing wormholes, those cosmic shortcuts bending space and time. According to Einstein's equations, a wormhole's throat would collapse instantly under its own gravity, unless it's propped open by something with repulsive properties, something like negative energy. It's the cosmic equivalent of using antigravity to hold open a tunnel through reality itself. But where would such exotic energy come from? The quantum vacuum offers a clue. Virtual particles constantly flicker in and out of existence, borrowing energy from the vacuum in fleeting bursts. Under certain conditions, like squeezing the vacuum between ultra-reflective plates in the Casimir effect, these fluctuations can create regions where the energy density dips below zero. It's as if the universe allows for tiny pockets of less than nothing, where the rules of classical physics take a backseat to quantum weirdness, the catch. These effects are microscopic and fleeting. Scaling them up to hold open a traversable wormhole would require engineering feats beyond our current grasp, perhaps even technologies that harness dark energy's repulsive force. The implications stretch far beyond wormholes. Negative energy could make time travel paradoxes a tangible dilemma. Some models suggest a time machine would need walls of negative energy to curve spacetime into closed loops, allowing you to meet your past self. But here's the twist: quantum mechanics might forbid such blatant violations of causality. The chronology protection conjecture proposes that the universe has a built-in defense mechanism, a kind of quantum immune system that prevents time travelers from rewriting history. Negative energy could be the wrench in that system, or it might reveal new layers of cosmic law we've yet to uncover. Now shift gears to an even deeper mystery. Could negative energy hold clues to life itself? Some researchers speculate that quantum fluctuations, those same flickers that hint at negative energy, might have played a role in life's origins. The delicate balance of energy in early Earth's chemical soups could have been nudged by quantum effects, steering molecules toward self-replication. It's a fringe idea, but if true, it would mean the universe's most exotic phenomena aren't just out there in the stars. They're woven into the fabric of our existence, from the vastness of space to the spark of life in a primordial tide pool. Whether negative energy remains a mathematical curiosity or becomes the key to unlocking spacetime's greatest secrets, one thing is certain: it forces us to rethink the boundaries of the possible. The universe, it seems, keeps a few aces up its sleeve, and negative energy might just be the wild card we never saw coming. Quantum biology sounds like something ripped from a futuristic novel. Living organisms harnessing the bizarre laws of the quantum realm to thrive in our classical world. Yet mounting evidence suggests nature might have been exploiting quantum tricks for billions of years, long before humans even dreamed of quantum mechanics. Take photosynthesis, the process plants use to turn sunlight into energy. At its core lies an efficiency that baffles scientists. Nearly every photon absorbed is converted into usable energy, a feat our best solar panels can't match. The secret: quantum coherence. When light hits a plant's photosynthetic proteins, the energy doesn't hop randomly between molecules like a pinball. Instead, it spreads out like a wave, exploring multiple pathways simultaneously to find the quickest route to the reaction center. It's as if plants perform instantaneous quantum computations to optimize energy transfer, turning sunlight into sustenance with near-perfect precision. But plants aren't the only quantum adepts. Migratory birds navigate thousands of miles with pinpoint accuracy, even on cloudy days, a mystery solved by quantum entanglement. In their eyes, a protein called cryptochrome contains electron pairs that become entangled when struck by light. Earth's magnetic field subtly alters these entangled states, creating a chemical compass sensitive enough to detect the planet's weakest magnetic fluctuations. Picture a bird perceiving the world as a shimmering quantum overlay, where magnetic fields paint invisible highways across the sky. Then there's the enigma of smell. Traditional lock and key models struggle to explain how we distinguish so many scents with such nuance. Quantum tunneling might be the missing piece. When odor molecules bind to receptors in your nose, electrons tunnel through barriers inside the protein, triggering signals your brain interprets as specific smells. This would mean your morning coffee's aroma isn't just chemistry, it's quantum physics in action, with particles ghosting through barriers to create sensory magic. These discoveries raise a provocative question: is life itself a quantum phenomenon? Some researchers argue that evolution, faced with the relentless pressure to optimize, stumbled upon quantum coherence as the ultimate tool for survival. If true, the boundary between the living and the quantum worlds isn't just blurry, it might not exist at all. From the way enzymes speed up chemical reactions to the precision of DNA replication, quantum effects could be silently orchestrating life's most vital processes. Now shift your gaze beyond Earth to a force so pervasive it might knit the cosmos together. Dark energy's repulsive push dominates the universe, but what if it's not the only invisible player? Hidden fields and undiscovered particles could be weaving through the vacuum of space, shaping reality in ways we're only beginning to imagine. The quantum world doesn't end at the edge of a petri dish. It might be the unseen architect of everything, from the smallest cell to the grandest galaxy. Actions might sound like something from a physicist's wish list, but these elusive particles could hold the key to unlocking two of the universe's biggest puzzles. First, there's dark matter, the invisible glue holding galaxies together. Then there's the strong CP problem, a nagging inconsistency in quantum physics where the laws governing subatomic particles seem oddly lopsided. Actions, if they exist, could neatly explain both. Picture a cosmic janitor sweeping up the mess in our equations while quietly accounting for the missing 85% of the universe's matter. It's an elegant solution, but finding proof is like searching for a whisper in a hurricane. These hypothetical particles were first dreamed up in the 1970s to explain why the strong nuclear force, the one binding protons and neutrons, doesn't seem to care about the direction of time. Unlike other forces, it treats left and right, past and future with perfect symmetry. That's mathematically beautiful, but it clashes with observations. Actions would restore that balance, acting as nature's reset button. But here's the twist: to do their job, they'd need to be incredibly light, barely interacting with ordinary matter. That makes them perfect dark matter candidates, particles drifting through walls, planets, even you, without a trace. The hunt for actions is a masterclass in scientific creativity. In underground labs cooled to near absolute zero, researchers deploy super-sensitive detectors bathed in powerful magnetic fields. The idea: if actions exist, those magnetic fields could coax them into transforming into faint photons, particles of light, leaving a detectable signal. It's like turning an invisible ink message visible under just the right kind of light. One experiment, the Action Dark Matter Experiment, or ADMX, uses a high-tech radio tuned to the frequency actions would emit if they converted. So far, silence, but the search is far from over. Meanwhile, astrophysicists scan the cosmos for indirect clues. Some theories suggest actions could cluster around black holes, emitting faint radio waves as they decay. Others propose they might subtly alter the light from distant neutron stars. Even our own sun could be a factory for these particles, streaming them into space like an invisible solar wind. The challenge is separating these hypothetical signals from the universe's endless background noise. What if actions aren't just particles, but a cosmic symphony? Some models suggest they could condense into vast, wave-like structures, rivers of dark matter flowing through galaxies, sculpting the universe on scales we're only beginning to map. It's a breathtaking vision, an invisible dance of particles so light, so pervasive, they've shaped the cosmos since the first moments of the Big Bang. The stakes couldn't be higher. Discovering Axions wouldn't just fill a gap in our theories, it would rewrite them. They could be the bridge between the quantum world and the cosmos, the missing link in a grand unified theory of everything. Or they might be another dead end in a universe that loves to keep its secrets. Either way, the search forces us to ask, what else is hiding in the shadows, quietly shaping reality while we struggle to see it? The holographic principle turns our perception of reality inside out. What if the three-dimensional universe we experience is just a shadow cast by information scribbled on a distant, two-dimensional surface? This isn't science fiction. It's a radical theory born from the fiery depths of black hole physics. Picture a black hole's event horizon, the point of no return where light and matter vanish forever. In the 1970s, physicist Jacob Bekenstein made a startling discovery. The area of a black hole's horizon isn't just a boundary, it's a ledger, recording every bit of information about the objects that fell in. Like a cosmic hard drive, the horizon stores data in tiny, Planck-sized pixels, with each pixel holding a binary yes or no answer about the universe's state. Now, stretch this idea to the entire cosmos. The holographic principle suggests that everything we see, stars, galaxies, even the space between them, is a projection from a two-dimensional surface at the edge of the observable universe. Think of it like watching a 3D movie. The depth and motion feel real, but they're just illusions created by light patterns on a flat screen. In this case, the screen might be the boundary of the universe itself, with the laws of physics acting as the projector. The math behind this is staggeringly elegant. When physicists calculate the maximum entropy, the total information capacity of a region of space, it scales with its surface area, not its volume. That's like saying the data stored in a room depends on the wall's square footage, not the cubic space inside. It hints that the true, real estate of reality isn't the space we move through, but the surfaces enclosing it. But how could this possibly work? One clue lies in quantum entanglement. Particles on the boundary might be entangled with those in the bulk of space, creating a web of connections that stitches the 3D illusion together. It's as if the universe is a vast, dynamic tapestry, with threads of information weaving the fabric of reality from the edges inward. The implications are mind-blowing. If the holographic principle holds, it could unify gravity and quantum mechanics by showing that gravity isn't a fundamental force, it's an emergent phenomenon, like temperature arising from the motion of atoms. Even time might lose its status as a fundamental ingredient, emerging instead from the way information flows across the cosmic boundary. Skeptics argue that testing this idea seems impossible. How do you probe the edge of the universe? Yet, subtle signatures might lurk in the cosmic microwave background, the afterglow of the Big Bang. Certain patterns in this ancient light could reveal whether space-time is truly pixelated at the tiniest scales, like a digital image viewed up close. Other experiments hunt for anomalies in high-energy particle collisions, where the fabric of space might glitch like a hologram under stress. Whether the holographic principle is proven or not, it forces us to confront a humbling possibility. The universe might be far stranger, far more interconnected than our senses suggest. We could be living inside a cosmic Matryoshka doll, where every layer of reality is just another level of the illusion, and the truth is written in code on a surface we'll never see. Time crystals sound like something from a physicist's wildest dream, structures that pulse and oscillate without any energy input, defying the universe's relentless march toward disorder. Unlike ordinary crystals, which repeat their patterns in space like a grid of atoms in a diamond, time crystals repeat in time, cycling through states like a perpetual motion machine that somehow sidesteps the laws of thermodynamics. The idea was first proposed in 2012 by Nobel laureate Frank Wilczek, and for years it was dismissed as impossible. After all, how could something keep moving without energy, violating the sacred rule that entropy always increases? Yet in 2017, researchers did the unthinkable. They created time crystals in the lab, using chains of charged atoms chilled to near absolute zero and nudged with precise laser pulses. What makes these bizarre structures so revolutionary? For starters, they're the first confirmed example of a non-equilibrium phase of matter, a material that never settles into thermal equilibrium, the state where all energy is evenly distributed. Imagine a pendulum that swings forever without friction or a clock that ticks without winding. Time crystals achieve this not by breaking physics but by exploiting quantum loopholes. Their atoms become locked in a dance of entanglement, synchronizing their flips in a way that's immune to energy loss. It's as if they've found a hidden groove in the fabric of reality, a rhythm that even the universe can't dampen. The implications are staggering. In quantum computing, where fragile qubits lose coherence in a blink, time crystals could act as perfect memory cells, stable, self-renewing states immune to decoherence. They might even hint at new phases of matter we've yet to imagine, like space-time crystals, with patterns woven across both dimensions. But the real puzzle is what time crystals say about time itself. Thermodynamics insists time has an arrow, a one-way flow from order to chaos. Yet here's a system that seems to dance in place, cycling without decay. Could time crystals reveal a hidden symmetry in time, a layer where the past and future are more fluid than we thought? Now, shift your gaze to a force so fundamental it might stitch the universe together. The Grand Unified Theory, a single framework explaining gravity, electromagnetism, and the nuclear forces, has eluded physicists for decades, but hidden in the quantum foam, there might be a thread connecting them all. For centuries, physicists have chased a dream so audacious it borders on alchemy, uniting all the forces of nature under a single, elegant framework. Electromagnetism lights our cities and powers our devices. The strong nuclear force glues atomic nuclei together, while the weak force drives radioactive decay. And gravity, the most familiar yet most mysterious of all, shapes the cosmos on the grandest scales. These forces seem utterly distinct, each with its own rules and particles. But what if they're just different faces of the same primordial power, fractured during the Big Bang like shards of a cosmic mirror? This is the quest for a grand unified theory, a master equation that could reveal the hidden unity beneath reality's surface. The first clues emerged in the 19th century, when James Clerk Maxwell wove electricity and magnetism into a single electromagnetic theory. Later, the Standard Model combined electromagnetism with the weak and strong forces, painting three of nature's four forces with the same quantum brush. But gravity stubbornly resists inclusion. Einstein's general relativity describes it beautifully as the curvature of space-time, while quantum mechanics governs the subatomic realm with probabilistic flickers. The two theories clash violently at extremes like black holes or the universe's birth, where infinite densities and quantum fluctuations collide. Bridging this divide isn't just academic. It could unlock secrets from the Big Bang's first moments to the fate of the cosmos. Enter supersymmetry, one of the most promising candidates for unification. It proposes that every known particle has a hidden superpartner with subtly different properties. Electrons might pair with selectrons, quarks with squarks, all dancing through extra dimensions we can't perceive. If correct, supersymmetry would smooth the jagged edges between quantum forces and gravity, offering a path toward unity. The math is breathtakingly elegant, but nature hasn't yet cooperated. particle colliders like the Large Hadron Collider have hunted for these superpartners for years, with no definitive sightings. Some theorists argue they're just too massive for current technology to detect. Others whisper that supersymmetry might need rethinking, yet the dream lives on in even wilder ideas. String theory imagines particles as vibrating strings, their harmonies generating all forces and matter in a 10-dimensional symphony. M-theory posits a web of interconnected membranes floating in a higher dimensional space. And loop quantum gravity sketches spacetime as a network of interwoven loops where gravity emerges from their quantum tangles. Each approach has its triumphs and pitfalls, but they share a common thread: the conviction that unity lies hidden, waiting to be uncovered. What makes this search so thrilling is the possibility of discovery lurking just beyond our grasp. The moment we detect a particle or phenomenon that fits one of these theories, the puzzle pieces could snap into place with dizzying speed. Imagine waking up to headlines that the LHC has spotted a graviton-gravity's hypothetical quantum carrier, or that astrophysicists have found evidence of extra dimensions in cosmic microwave patterns. The ramifications would ripple through science, technology, even philosophy, reshaping our understanding of reality itself. But until then, the grand unified theory remains physics' holy grail, a beacon drawing us toward a deeper truth. Whether the answer lies in supersymmetry, strings, or something entirely unforeseen, one thing is certain: the universe doesn't play by separate rules. It's waiting for us to decipher its hidden code, written in the language of forces we're only beginning to understand. And when we do, we might find that gravity, electromagnetism, and the nuclear forces were never truly apart, just different notes in the same cosmic song. Neutrinos are the universe's ultimate shape-shifters, particles so elusive they pass through entire planets like ghosts, yet so abundant that trillions stream through your body every second. But here's the twist: these cosmic phantoms don't stay the same. As they race through space at nearly the speed of light, neutrinos spontaneously morph between three distinct flavors: electron, muon, and tau. This bizarre metamorphosis, called neutrino oscillation, is more than just a subatomic magic trick. It's proof that neutrinos have mass, a revelation that shattered the standard model of particle physics, which had long assumed these particles were weightless. The discovery came from an unexpected place: the Sun. For decades, scientists puzzled over why Earth detected far fewer electron neutrinos from solar fusion than theories predicted. The answer: those missing neutrinos weren't gone. They'd simply changed costumes mid-journey, transforming into flavors our detectors couldn't see. It's as if you mailed a letter written in English and it arrived in French with no translator in between. To catch these oscillations in action, physicists built colossal experiments like Japan's Super Kamiok and a tank filled with 50,000 tons of ultra-pure water, lined with sensors waiting for the faint blue glow of a neutrino collision. Deep underground, shielded from cosmic noise, these detectors watch for the telltale flickers that betray a neutrino's identity crisis. But why does this matter? Because neutrino oscillations hint at a reality far stranger than the standard model allows. If neutrinos have mass, even a tiny one, there must be undiscovered physics at play, perhaps new particles or forces that interact with them in ways we've never imagined. Some theories suggest neutrinos could be their own antiparticles, a property that might explain why the universe has more matter than antimatter. Others propose that sterile neutrinos, even more elusive than their known cousins, could be hiding in plain sight, weaving through dimensions we can't access. The implications stretch from the quantum realm to the cosmic scale. Neutrinos born in the Big Bang's aftermath might hold clues to the universe's earliest moments, their oscillations encoding secrets about how matter triumphed over antimatter. Meanwhile, high-energy neutrinos from distant supernova act as cosmic messengers, their flavor shifts revealing the density of space they've traversed. It's as if these particles are whispering a coded language, one we're only beginning to decipher. What makes neutrinos truly extraordinary is their refusal to fit neatly into any box. They're not just particles, they're puzzles wrapped in enigmas, each oscillation a flicker of something deeper lurking beneath the surface of reality. And as we peel back those layers, we might just find the keys to understanding everything from the tiniest quantum fluctuations to the grandest structures in the cosmos. The universe, it seems, has a way of hiding its most profound truths in the most elusive places. Cosmic inflation is the universe's ultimate magic trick, a fleeting moment when space itself stretched faster than light, smoothing out every wrinkle and flaw in the cosmic fabric. Picture a balloon inflating from subatomic size to larger than the observable universe in less than a trillionth of a second. This wasn't just rapid expansion, it was exponential, a runaway explosion of spacetime that left the cosmos eerily uniform in temperature and density. Without inflation, the universe would be a chaotic patchwork of hot and cold spots, with no galaxies, no stars, and certainly no us. But here's the puzzle. What flipped the switch on this brief, unimaginable burst of growth? The leading theory points to a mysterious field called the inflaton, a kind of cosmic adrenaline that flooded the early universe with negative pressure, forcing space to expand at an accelerating rate. As the inflaton's energy decayed, it reheated the universe, filling it with the particles and radiation that would eventually form atoms, planets, and everything else. Think of it like a sprinter who dashes at breakneck speed, then suddenly stops, leaving behind a cloud of dust that settles into the world we know. But the inflaton isn't just a theoretical placeholder. If it exists, it should have left fingerprints in the form of primordial gravitational waves, ripples in space-time that would have echoed through the universe like a cosmic gong. Detecting these waves would be like finding the first frame of the universe's home movie. Experiments like BICEP and the upcoming Light Bird mission scan the cosmic microwave background, the afterglow of the Big Bang, for telltale swirls called B-mode subtle twists in polarized light that could betray inflation's violent birth pangs. So far, the signals have been elusive, drowned out by interstellar dust or perhaps hinting that inflation was quieter than we imagined. But if we do catch them, it would confirm not just inflation but the existence of quantum gravity itself, linking the infinitesimal to the infinite. Yet inflation raises as many questions as it answers. Was it a one-time event, or does it happen endlessly, spawning new universes in a vast multiverse? Some theories suggest our cosmos is just one bubble in an eternal froth of inflating spaces, each with its own laws of physics. Others propose that inflation didn't smooth the universe perfectly, that tiny quantum fluctuations were stretched into the seeds of galaxies, meaning the largest structures in the cosmos owe their existence to subatomic randomness. Now shift your gaze to a phenomenon that challenges reality's very foundation. Quantum decoherence asks why the weirdness of the quantum world particles in multiple states, cats both alive and dead, collapses into the concrete reality we experience. The answer might lie in the universe's most subtle interactions, where observation isn't just a measurement but a negotiation between the possible and the actual. What if everything you know, the stars, the laws of physics, even your own thought, is just an elaborate simulation running on some advanced civilization's supercomputer? The simulation hypothesis isn't just science fiction anymore. Serious thinkers, from philosophers like Nick Bostrom to tech visionaries like Elon Musk, argue there's a startlingly high probability we're living in an artificial reality. Their reasoning starts with a simple assumption. If any civilization ever reaches the technological capacity to create hyper-realistic simulations of conscious beings, and if they choose to run countless iterations of those simulations, the number of simulated minds would vastly outnumber biological ones. Statistically speaking, you're far more likely to be one of those simulated beings than an organic one in the real world. But this isn't just a numbers game. Quantum mechanics adds eerie credibility to the idea. Take the observer effect, where particles seem to choose a state only when measured. Could this be a cosmic optimization trick, a way for the simulation to render reality only when needed, saving computational power? Or consider entanglement, where particles communicate instantly across vast distances, defying the speed of light. Some theorists suggest this spooky action might be a sign of underlying code shortcuts, like two variables in a program sharing the same memory address. Even the pixelation of space-time at the Planck scale could hint at a finite resolution, the universe's equivalent of a rendering limit. Critics counter that these phenomena have plausible explanations within standard physics, and the simulation hypothesis is untestable by nature. But proponents point to potential glitches we might uncover. For instance, if the simulation has constraints, certain high-energy physics experiments could reveal inconsistencies in the laws of nature, like rounding errors in a mathematical model. Others suggest looking for signs of deliberate constraints, such as limits on small-scale energy measurements that might expose a simulated grid. The implications are dizzying. If we're in a simulation, does the simulator interact with us? Are there layers, simulations within simulations? And what happens if we ever develop our own conscious simulations? The hypothesis doesn't just challenge our place in the cosmos. It reframes reality itself as something malleable, even contingent. Whether it's true or not, the mere possibility forces us to confront the deepest questions about existence, consciousness, and the nature of the universe. And that, perhaps, is its greatest value, not as a definitive answer, but as a mirror held up to the limits of human understanding. Now we arrive at the final frontier of cosmic mysteries, where all these threads converge into a single, haunting question. What is reality, truly? The answer, if there is one, might lie beyond physics, beyond philosophy, in a truth so profound it redefines everything we think we know. Consciousness might be the ultimate wild card in the quantum deck, an observer that doesn't just witness reality but actively shapes it. Picture Schrödinger's cat again, suspended between life and death until someone opens the box. But here's the unsettling twist. What if the act of observation isn't just a passive measurement, but the very thing that forces the universe to make up its mind? This idea, known as the von Neumann-Wigner interpretation, suggests consciousness isn't a byproduct of physics, it's a player in the game, collapsing quantum possibilities into concrete reality. It's as if the universe hesitates until a mind looks, then scrambles to present a coherent world. The implications are staggering. If consciousness plays this role, then the boundary between observer and observed blurs beyond recognition. Take the double-slit experiment, where particles behave as waves until measured. Some theorists argue it's not the detector that collapses the wave function, it's the moment a conscious being registers the result. This isn't just philosophy, it's a testable hypothesis. Experiments like the quantum Zeno effect show that constantly observing an unstable particle can prevent it from decaying, as if attention itself freezes reality in place. But how far does this ripple extend? Could the collective observation of billions of minds, human or otherwise, shape the universe on larger scales? The anthropic principle hints at something eerily similar. The laws of physics seem finely tuned to allow conscious life to exist. Is that mere coincidence or evidence of a deeper symbiosis between mind and cosmos? Some radical theories propose that consciousness isn't confined to brains at all, that it's a fundamental property of the universe like space or time. In this view, stars, galaxies, even the vacuum itself might possess a rudimentary form of awareness, woven into the fabric of reality. This brings us full circle to entanglement, where particles remain linked across vast distances. If consciousness is part of the equation, could entangled particles know when they're being observed, no matter how far apart? It's a notion that borders on the mystical, yet it emerges from cold, hard math. The universe might not just be interconnected, it could be alive in ways we're only beginning to fathom. So where does that leave us? Perhaps reality isn't a fixed stage, but a dynamic dance between mind and matter, where every observation is a step in the choreography. Whether consciousness is the composer, the dancer, or the dance itself remains one of the greatest mysteries, one that might finally bridge the gap between quantum weirdness and the world we perceive. And if that's true, then the act of wondering about the universe might be the universe wondering about itself. From the spooky embrace of quantum entanglement to the relentless push of dark energy, these 22 phenomena peel back the curtain on a cosmos that defies every expectation. Each discovery doesn't just answer a question, it ignites a dozen more, fueling humanity's endless curiosity. Think of it like standing at the edge of an infinite labyrinth. Every turn reveals new corridors, new doors begging to be opened. And that's the beauty of it. The universe isn't a puzzle to be solved. It's a conversation, one where nature whispers secrets we're only beginning to decode. Consider how far we've come. A century ago, quantum mechanics was a fringe idea. Dark matter wasn't even a hypothesis, and the notion of time crystals would have been dismissed as fantasy. Today, we're grappling with realities that sound like they're ripped from the pages of a sci-fi novel. Yet for all our progress, we've barely scratched the surface. What lies beyond the standard model? Could wormholes truly be cosmic shortcuts? Is consciousness somehow woven into the fabric of reality? The questions grow wilder, but so do the possibilities. This isn't just science, it's storytelling on the grandest scale. Every experiment, every observation adds a sentence to the epic tale of the universe. And you're part of it. Whether you're a casual stargazer or a physics enthusiast, these mysteries belong to all of us. They remind us that wonder isn't just for textbooks. It's in the night sky, the glow of a smartphone, even the air we breathe. The quantum and the cosmic aren't distant abstractions, they're the hidden rhythms of everyday life. So as we close this journey, here's an invitation. Keep looking up, keep asking why, and never let the world convince you that magic is gone. The universe is still writing its story, and the next chapter might be the most astonishing yet. Drop your favorite phenomenon in the comments. Was it the eerie dance of entanglement, the phantom grip of dark matter, or something else entirely? And if you're hungry for more deep dives into the unknown, hit subscribe. The cosmos has plenty more surprises up its sleeve, and we're just getting started.